Okay, so hi to you all. We meet again. This is our sixth lecture, and I will keep talking about the main ingredients of the proof of MIP star is equal to RE. So at the previous lecture, we talked about the compression theorem. We stated this compression theorem, and we deduced from the compression theorem the fact that RE is contained in MIP star. And since this is such a strong theorem, it is quite hard to prove the compression theorem. So we are reviewing the main ingredients that are part of this compression theorem. Like, this is the goal of this lecture. And today I'm going to talk about maybe technically the hardest part. Okay, so we start from the technically hardest, and then we will talk about other very smart and ingenious ideas that come also later, but a bit less technical. Like, the part of the proof that I'm going to review right now actually consists of about 180 pages of the appendix of the new paper and an additional 120 paper, which was part of the fix that they published recently. So in this sense, we will talk only about part of the technical parts and not all of them, of course, but this is the technically heavy part. And then we will talk about answer reduction or equalization, parallel repetition, probably next week, because what I'm planning for today is already 31 slides, and probably we will also not finish this part. Okay, so also I want to talk about the rest of the semester. So we are planning to do, this seminar is a yearly seminar, but we will do it only during the semester, the Israeli semesters. So we finish at, okay, so I put here, so my calendar. So the last week of the semester is the, wait, I'll tell you, the 10th of January will be the last time we meet for this semester, and then we will resume at some point in March, okay? So I will tell you all the correct details when they'll come, but the plan for, at least for now, is the following. So we will finish this review of the main ingredients. Then we will talk about some more technical parts, so Nymax dilation, which enables us to go from POVMs to PVMs, from positive operator valued measures to projective valued measures. Then we will talk about error correcting codes, about Reed-Muller codes and low degree tests. We will prove the PCP theorem and actually a specific version of it that they need in their paper. So we will need to be specific. And then we will talk about the fact that the set CQC, the quantum commuting set of correlations, is closed. And together with that, talk about the fact that Cohn's embedding problem and Searson problem are equivalent, at least one of the directions that I think that, I'm not sure. Alon will talk about this, so maybe he will elaborate more when I'm finished. So this is the plan, at least for now. Maybe we'll do more, maybe we'll do less, it depends. Now, we have a problem, two problems, okay? So next week, there's Thanksgiving. So I would like you to tell me if this is a problem for you. I'm not sure whether there are any Americans in the audience, but if there are, and this is a problem for you, please inform me. So we will postpone the next week and not do a meeting. And also in 3 weeks from now, there is the psychometry in Israel, and the universities are officially on a break. So again, if this is a problem for you to meet at this, I'll tell you exactly what are the, so on the 29th is next week, and 3 weeks from now is the 13th of December. If any of this of these occasions is a problem for you and you prefer that we would not meet, please inform me, okay? So at least for now, I don't want to decide. I want to hear from you, and we will talk about it after we will get your input. Great. Any questions about any of the what I said? No? Great. Okay, so we go back to self-testing and introspection. So I will recall the idea. So I talked about it in the second hour last time, but I will review most of what I talked about last time in the second hour. So let's recall what we want to do. So there was, before this paper, before the MIP star is equal to RE, there was another paper called MIP star contains NEEXP. And in some sense, we talked about the compression theorem, and you can think of it as as a paper that can only compress once. Okay, so they had some compression theorem and they could only compress once. And the good thing about the MIP star is equal to RE is that you can do your compression iteratively. Okay, so I'm giving you a vague idea of what is the improvement in the MIP star is equal to RE. But I think the main idea here can be already seen in this paper, in the next is contained in MIP star. And the idea is the following. So you take the MIP protocol for the succinct 3 coloring problem. So you are given an exponentially large graph using some circuit. You need to decide whether it's 3 colorable. It was shown that by Babai, Fortnow, and Lund that this can be solved in MIPs using multi-prover interactive proofs. And you can use this, and it was shown by Ito and Vidic that the same thing works also in the quantum scenario. So the same protocol, only with 3 players, works in the quantum scenario. And you just take this protocol and you use it for the succinct 3 coloring problem. So now you're trying to decide whether a doubly exponential large graph is 3 colorable. Okay, so this is what you want to decide. You have a graph of this size. The input is of size n. The graph is of size 2 to the 2 to the n. And you want to decide about this graph whether it's 3 colorable. Okay, now if you use the protocol from the protocol of the succinct 3 coloring problem, you get some protocols. So you have players, you have a verifier, he sends questions, he gets answers, and so on. But instead of the questions and answers being polynomial in the size of the input, they are exponential in the size of the input. Okay, so you can read them as you did before. You can read the questions and answers, but they are too long for you to read. They are exponentially sized, so it will take you exponentially long time to send the questions, exponentially long time to read the answers and verify that they are correct. Okay, so this is the problem, and we will not talk about how to solve it completely. This will be next time probably, but the solution is what we discussed last time. It is called introspection. And the idea in introspection is quite amazing. And this is a truly quantum phenomenon. This is, you cannot, let's support, anticipate.
Expect.
Yeah, expect, thanks. You cannot expect such a thing to happen classically. This is, okay. And the method is as following. You send the long protocol, we said there are long questions and long answers. So now you replace the long questions by short questions, okay? So you ask only polynomially sized questions, but now you are still answered by long answers, and the long answers are formatted as follows. They are tuples, they are pairs of question from the long protocol and answer from the long protocol, and we interpret this pair as if we would have played the long protocol with the long protocol. You would have asked me the question X, and I would have answered the answer A. Okay, so this is how we interpret X comma A, and Y comma B the same. You would have asked me question Y, and I would have answered answer B. So the answers are still very long, but when we have long answers, we know that we can maybe use PCPs to reduce their size, to check them only probabilistically. So this part will be maybe easier. But shortening the questions is quite hard. So this is what we are going to talk about today. So this introspection is this idea. And at least in the case of the protocol for the succinct recoloring problem, the way the questions are constructed enables us to at least understand how do you force, okay, so what do you need to force the provers to sample the questions according to the distribution that you actually need, okay? So we need to force the provers to actually sample X and Y according to the distribution, and also in a way that they don't share information about like when A gets X and B gets Y, they need not to know about the other's question. Okay, so this is the goal. So let me just say that the questions in the protocol are just lines and points in some vector space over finite field of size a power of 2. Okay, so we need them to sample points and lines in some vector space with over some finite field of size power of 2. Okay, so to that end, I want to recall what is an EPR pair and how can it help me achieve this goal. So an EPR pair is just the following vector in the tensor product of C squared with itself. It's just 1, 0, tensor 1, 0 plus 0, 1, tensor 0, 1 divided by square root of 2. So this is the square root of 2 is just a normalization. This is a unit vector. And the two properties that are important to know about an EPR pair is the following. So recall that a measurement, okay, so this is a projective measurement, is just choosing a basis. And then okay, so I'll show it on R squared. So you choose an orthonormal basis, and you have, so this is the basis that you chose, and this is the unit vector that you have. And then when you measure this unit vector according to this basis, the probability that you will get each one of the results, so we will call one of the vectors 0 and one of the vectors in the basis 1. Okay, this is just a notation. This is not the 0th vector and the 1 vector. This is just names for the vectors. The probability that I'll get 0 is just the projection, the size of the projection on the 0th vector squared. And the probability that I will get the 1 answer is just the projection on the 1th vector squared. Okay, the size of the projection squared. And this is a measurement, okay? So, and the good thing about this specific vector, this psi, is that no matter what basis you choose, the probability of getting either of the results is equivalent. Okay, so you will, no matter what basis you choose, it will have a 50-50% chance of giving you either of the results, either a 0 or a 1, no matter how you call the vectors. Okay, so this is the first property. The second property is that if player A, so if player A measures according to one basis, and player B takes the same basis, this is important. Okay, so this is player A's side, and this is player's B side. So if A and B measure according to the same basis, they use the same basis measurement, they will get the same answer. So this is the consistency property. If they measure according to the same basis, they will get the same answer, but the answers will be distributed 50-50 between 0, 0 and 1 and 1, 1. Okay, and the important thing, it seems like it's basis dependent. We wrote here the vector as if it is dependent upon the basis that we started with. But if you check, you can see that moving to other bases, you get the same property. So it will look the same in every other basis. Okay, so this is the consistency property. So I'll say it again shortly. If they measure according to the same basis, they get the same result. Now, what is incompatibility? Now, maybe I can do it this again. No, I need to. Okay, now if incompatibility says that if player A is measuring according to some basis, and player B, okay, so maybe I'll take this thing, duplicate it again. And player B is measuring according to a 45 degrees rotated basis. Then it erases all the information about the first basis. So if one of them measures according to a basis and the other measures according to a 45 degrees rotated basis, it erases all the information in the first basis. Okay, and this just comes from this the property that I told you about measurements. Okay, so measuring according to a 45 degrees rotated basis just erases the information in the original basis, and this is a way of like hiding information one from the other. Like you can measure according to one basis and it will hide the information. Okay, so this is the idea, and actually we have only two bases that we care about. We have the original basis of the plane, so this is 1, 0, and 0, 1. This is called the Z basis. And we have the 45 degree rotated basis. So this is called, we have this thing, and this is called the X basis. And we will measure only according to these two bases, and then they are incompatible. So measuring according to one will erase things about the other.
Michael?
Yes.
Can I make sure for a second that I understand what you mean by if they measure? So again, the consistency was that if they use the same measurement, they get the same answer?
Yeah, this is consistency.
But only for phi, right?
Yeah. This is a property of, I call it psi. I'm sorry that it looks like phi. This is a property of the EPR pair, okay? And I'm not claiming something about, okay, so the incompatibility is the property of the basis, but the property of the EPR pair is the consistency, and the incompatibility is just something that I'm saying that if you measure according to incompatible bases, it erases information in the other bases. Okay, so measuring the X basis removes any information in the Z basis. So it makes every result in the Z basis equally likely.
Mm-hmm.
Yeah, so just to make sure that others also understand, this is a tensor product of two quantum bits. And so the consistency means that if one party has one bit and the other party has another bit, and they both measure using the same basis, each one measures their own bit, then they will get the same answer. This answer is 50-50. It can be either 0 or 1 with probability 50 each, but it's going to be the same answer for both.
Right. Okay, great.
Wait,
so
Guy, and incompatibility, since you started explaining, so what does incompatibility mean from the perspective that you described?
So if I have a bit and I measure with one basis and you have the other bit, but you measure according to a basis that is shifted by 45 degrees, or pi over 4 to sound more professional, then I get a random bit and you get a random bit, and there is zero correlation between the two measurements.
Okay, thank you.
Okay, thanks, Guy. So let me just model a way of thinking about a line, a random line and a random point on this line. So what is a line in F2 to the T vector space? It's just this thing, right? It has some point and you take all the, and there is a direction vector and there's a point on the line, and you take all the scalars times the direction vector and you sum them with the point that you start with and you get a line. So this is x plus, maybe this will work. No, doesn't work. Great. So this is the way we think of lines. And the point is just a point in the vector space, right? So what I'm claiming here is just that if you uniformly choose two vectors in f2 to the t to the m, okay, you get some point and some line where the point is on the line, and this is uniformly distributed. You need to take v to be non-zero, but it's okay if you measured it and you got 0, you just do it again, okay? And let's talk about what is the idea. So how would we check that the two players measure a line and the point in this uniform manner without cheating, okay? And this is a sketch. This is not very formal. It's the main idea, okay? The first step we need to do is we need to force the players to share two copies of 2 to the mt EPR pairs. Okay, so we have had this EPR pair that we talked about previously. We just need them to take 2 to the mt copies of this thing twice. Now I have the first 2 to the mt EPR pairs and the second 2 to the mt EPR pairs. And again, every player has only his part of the EPR pair. So as Guy said, there are the qubits that A has, and there are the qubits that B has, and but still they are entangled in this EPR pair definition. So A always get the left part of the tensor product, and B always get the right part of the tensor product. Okay, so what player A does, it measures, so A measures her part of the first 2 to the mt EPR pairs according to the Z basis. What does player A get? She gets exactly the point X, right? You agree if she measures the first 2 to the mt EPR, we didn't have X yet, right? The fact that she measures according to the Z basis, these 2 to the mt EPR pairs is what generates a uniform point inside the space, right?
She just gets m times t random bits, and then you just look at them as m t tuples of bits, which is a point in the space that you're interested in.
Yeah, exactly. But the fact that she measured it means that she sampled it. Okay, so already I didn't sample the point. She samples the point, right? She measures according to this Z basis. She samples the point. Now B does the same. But he just checks what is V. So he samples. He checks he measures according to the Z basis all the second 2 to the mt EPR pairs. Okay, so again, as Guy stated, B gets some long tuple of bits, and he interprets this bit as V. Okay, so this is a long tuple and interprets it as V. But then I want to check that B will know a point, will get a point on the line, but not necessarily X. We want him to get some equally distributed point on the line, but not get exactly X, because then he will know for sure that this is the point that player A got, right? So the way we force him to not know exactly which point on the line he gets is exactly taking this measurement that I call X to the power of V, okay? And this is some measurement that exactly erases any information about the Z part that is correlated with V. So you will lose any information about where exactly you are on the line. But if you then measure everything according to the Z basis, you will get some uniformly distributed point on the line. Okay, so this is a way of erasing.
Michael, can you explain again what is X to the power of V?
Yeah, I don't really want to explain what X to the power of V. You have these tensor products of X's, right? You get, okay, so I actually want X to the tensor of V. which we interpret as at each point where there is a 1, I measure according to the, no, I need something a bit more precise.
So let me ask, do you measure all empty qubits, or is it that you measure?
The problem is as follows. If V, okay, so I talked about it last time. If V was just the 1, 0, 0 vector, this is easy. I will just tell you, measure the first T coordinates according to the X basis, okay?
Mm-hmm. Okay.
Right? It will erase everything about the first coordinate, and then measure everything according to the Z basis, and then you will get all the information except the specific first coordinate, and you will get a uniformly distributed point on the line, right?
Mm-hmm.
So I need an analog of this.
Just
so I need to actually, Michal, yes, maybe.
It's just for you, it's just measuring the syndrome of V on this. So it's X multiplying the -1s.
So it's X if VI is 0, and it's Z if VI is 1? No?
No. If it's 0, it's
no.
identity, and if it's 1, it's X.
Sorry, if it's 0 is what?
It's identity.
It's the identity.
Okay. Okay. So you just measure the coordinates where it's 1.
Take the XOR.
Yeah, but I measure them together.
And then take the XOR. Okay.
Yeah. Okay, cool. Okay, so
wait.
Now this is also a bit lying, because you cannot actually do this because then he gets some information. If he both measures this X and then measures according to the Z, he gets some information about the point small x. But the actual protocol is a bit more complicated. But let's, this is just kind of a brief to understand the main idea. So you do some kind of this hiding using incompatible bases, and then it erases the information in the other bases. Yes, Guy, maybe you wanted to clarify another thing.
Yeah, I'm not sure. You said something about XO, which I don't understand. But the point is that you want, the point of this mock idea, which is not the right thing, I guess, is that—
It's almost the right thing.
What?
It's almost the right thing. You probabilistically sometimes tell them to measure the X thing, sometimes tell them to measure the Z thing, but you can think of it as if you just tell them this protocol. Okay, anyway, just
okay. So whenever V is 1, it means that
1 0 0 0 0 0. What do you mean by 1?
In every, so okay, I'm trying to see if I understand what you're saying. So what you're saying is that when in all coordinates where V is 1, you measure the coordinate in the first tuple of bits with basis X,
right?
And whenever,
but you don't do it bit by bit. You do it simultaneously. You take this operator X tensor I when you need X and when you need I, and you measure according to this. It defines a measurement, and you measure according to this measurement.
Yeah, why does it make any difference if you do it all at once or one bit at a time?
Okay, so
you don't want to measure. You don't actually want to collapse.
Yeah, exactly.
It says measure, so...
Yeah, but if you measure, it's a partial measurement. You just measure if all the bits, it's like measuring just the parity of something. So it's, if you have a superposition of over many strings, then you just measure the parity, then the remaining state is still a superposition of all strings with that parity. And you don't want to collapse between those different strings.
Okay, wait, so you're just measuring the parity of the first tuple of bits, but not the parity of all of them, just the parity of
all the positions where the X is, the V is 1. I
see, okay.
Yeah, right. And also it's not exactly the parity because it's in the X basis, so it's the parity, in a rotated basis.
Yeah, okay. Right.
Is there a chance for the rest of us to understand, or We should just be.
Yeah. Let me try to say something.
Yeah, Dorit.
So let's just think for a moment about measurement in the Z basis. Okay. I wasn't here in the previous lectures. I don't know.
We know. Also, you were absent in the first few minutes, and I made fun of you.
Okay, so the Z basis is measuring the Z basis is basically just measuring whether the bit is 0 or 1.
Okay.
So now of course, if you measure a single bit in the Z basis, then you measure its parity.
Right.
Okay, so now suppose you want to measure the parity of 2 bits.
Okay.
So what you actually can do is you can measure in quantum language, this is just measuring the operator Z tensor Z.
Okay.
Because Z tensor Z, well, its eigenvectors are just either 1 or -1. And this only depends on the parity.
Values.
The eigenvalues, sorry.
Yeah, if you get a 1, you know that they are the same parity, and if you get a -1, you know that they are with opposite parity.
Okay, thanks.
Okay, so
we will talk about it in a moment, like actually.
So the meaning of x to the power v is just to measure the operator x. Sorry, let's stay with z. So the meaning of z to the power v is just measure the operator z tensor z only on those coordinates where v is 1.
Okay.
Which means just measure the parity of those coordinates.
Okay.
Okay. Which means once you measure just the parity, that means that that you don't measure anything else. Meaning you stay in a superposition over whatever was there with that parity.
Mm-hmm.
Okay.
Right.
So now the only difference here is that you're measuring x to the power v. But x to the power v is just like z to the power v. I mean, it's x and z are the same, except they are related by the Hadamard basis. So therefore, the Fourier transform of one of another.
Mm-hmm.
Yeah, so, and like in the Fourier transform, if you collapse a coefficient to something, it blurs out everything in the other basis, right? So you can think of it as if measuring something in the after you do the Fourier transform, knowing it for sure erases all the information after you do the Fourier transform. It mushes out all the results.
So to put it simply, I mean, maybe not intuitively, but very simply, technically, you first apply the Hadamard transformation on each one of the qubits. Then you measure in that parity in the Z basis, meaning you just measure the parity of the bits. And then you apply the Fourier transform again.
Right.
Nati, does this?
Yeah, certainly makes sense. Yeah, thank you.
To be precise, you apply the inverse of the Hadamard transform, but for 2 qubits, for a qubit, it's the same.
Okay, so I think at least we got the idea.
Michael, I'm not sure that this discussion was. So there is, I think, one thing which is even more basic, that somehow until now, this is not exactly how we talked about measurement, right? We talked about projection valued measurement, and now we are talking about a measurement with respect to a transformation.
Yeah, but you should think of the following. If you have a unitary, for example, and it has eigenvalues, think of the measurement that projects on the eigenspaces of the eigenvalues. So this is just what I want people to have in their minds.
Right, so now a measurement with respect to a transformation is a measurement with respect to the projections on the eigenspaces of this transformation.
Right, correct. We will get to it. We will just, this was supposed to be some brief thing, and we will go now to the details, and then we will see all
Michael,
most of the remarks that we had here. Yeah,
can I just ask one more question about the thing that you said about the fact that A and B shouldn't be correlated or shouldn't know about each other.
No, they should be correlated, but only in the following sense, that one of them gets a line, and so to get a line, you need a direction vector and the point on the line, right? I just want the point on the line to be uniform, although the other player has some specific point that he got, right?
Yeah, and that is why A measures in the Z basis and B measures in the X basis.
And only some of the information on the X basis, right? So B measures some of his information on the using the X basis, but then he measures also on the Z basis because he needs to know everything except for the exact position on the line, right?
I see.
He does need to know what specific line it is. So
okay, good,
great. Okay, so I will, as I stated, when we get to it, to the more technical, the correct way to do this, it's a bit more complicated in the sense that this is a game and you need to sometimes force them to measure this thing and sometimes force them to measure this thing, but at least the main idea is here. So this is good. But the main question is, okay, so the first point in the idea is force A and B to share many EPR pairs. And I remind you, the questions are short. So we need to somehow force them to share exponentially many EPR pairs by only using polynomially sized questions. So this is now our goal. I'm going only to talk about the first point of this idea. Great. And the way I'm going to talk about this idea is using the CHSH. So we finished the last talk by starting to analyze this CHSH game, but let's recall, first of all, what is the game, and then at least the analysis that we had at the end of last time, and then I will dive into the analysis. So the goal of this thing is to show you that to win the CHSH game, the players must share an EPR pair. Okay, so optimal strategy implies the players share an EPR pair. Okay, so this is the goal of the second hour, but let's start at least this analysis. So what is the CHSH game? First, we stated that it's a game where the questions and answers are just single bits. So the questions are either 0 or 1, and the answers are either 0 or 1. The distribution of questions is uniform, so you send either 0, 0, 0, 1, 1, 0, or 1, 1 with equal probability. And the winning predicate is the following. It is a winning condition if and only if the sum of the bits, so the XOR of the bits, okay, so the sum modulo 2, is the same as the product of the questions. The sum of the answers should be the same as the product of the questions. Okay, so this is a very simple game, at least it seems like a very simple game. And now we want to analyze some strategy that wins with the maximal possible probability. So we are also going to show now that the best possible winning probability of this game is this half plus 1 over 2 square root of 2. We stated that this is a result of Tzirilson. And then we want to say something structurally about the measurements, these M's and N's that are used here to measure the as measurements. Okay, so we have this M00, M01, M10, and M11. These are the POVMs of A, and these are and there are these N's that are the POVMs of B. So if you don't remember what a POVM is, so the MIJs and NIJs are positive semi-definite, and the sum M0I is the identity, and so the sum M1I is the identity, and so the sum N0I is the identity, and so on. So this is a POVM. Okay, great. And this psi is just a unit vector in CD to tensor CD. Okay, so this is the basic thing we have here. So what Guy stated, we said that there is this connection between taking a general matrix and thinking of it as a measurement by thinking of the projections on the eigenspaces of this matrix. Okay, so I'm just going to construct such a thing. Okay, so at least when these POVMs are not POVMs, but PVMs, when these are projections, these MIJs and NIJs are not positive semi-definite. So I'll replace that color. When they are projections, this A naught is exactly the space with the eigenspace of 1 is exactly the space that is projected by M00, and the eigenspace of -1 is the space projected by M01. And the fact that M00 plus M01 is the identity means that this is exactly a decomposition of the space into two orthogonal subspaces. One of them we think of as eigenspace 1, the other we think of eigenspace -1. Okay, so these are the A0, A superscript 0, A superscript 1, B superscript 0, and B superscript 1. And we stated last time that you need to check that A0 is self-adjoint, and also A0 squared is the identity. Okay, and this is just a straightforward calculation. This is only in the case of the projections. So this is in the orange case. And these are projections. These two things are satisfied. The first thing is satisfied also when these are not projections, since the positive semi-definite operators are already self-adjoint, right? So the first condition is in general. The second condition is only when these are projective measurements. Okay, great. So before we go before we take a break, I want to define to you the following operator. So you can take these three observables, okay, so this is N00 minus M01, and this is N00 minus N01, and you take the tensor of them and you take this specific sum, okay? So when you have in the superscript a 0, you take it with the plus sign. And if both superscripts are 1, I take it with the minus sign. And if you don't know this matrix beforehand, this operator beforehand, I want to ask you what is nice about this operator. So let's take a break, and you can think about what is nice about this operator, and how is this operator related to the CHSH game during the break. So we will resume at 5 o'clock as usual.
Hi, Michael. I want to be sure that I understand how the game is going and everything. So there are actually two kinds of questions, right? There are the question, okay,
I'm missing.
Okay, say you want to examine, I don't know, a graph coloring or something like this. So the X and Y, according to which they choose the operators, are related to the problem that you try to solve, right? And there are these queries that are part of the state vector that they share.
Okay. Go a bit slower. What was
So first, you have like the instance of the problem that you work on. You have a graph and you want to find a coloring for it or something like that.
Okay. You talk about the protocol from the beginning. Okay.
Yes. So now by X and Y, the different
X and
Y define XY, even XY, A and B define a certain game with a certain value that relates to this instance.
Right, exactly. Okay, exactly. There is a protocol such that if you play with it, if the graph is colorable, it's value 1. If the graph is not colorable, it's value bounded from 1/2, bounded from above by 1/2. But the problem with this protocol is that the questions and answers are too long.
Yes. So you use the state that they share to do, they use it to do queries actually on different lines, and
you should think of them as sampling the questions X and Y. I force them to sample the questions X and Y
yes.
such that I don't need to know originally. Like I just know that they sample it in an honest way. So I need to somehow to force them to sample the questions X and Y in some honest way without sharing information and using the distribution that actually comes from the original protocol.
Yes, and okay, so the fact that you talk about X and Y in both cases is a bit confusing, but okay. But
no, I ask questions. I don't understand. You mean in the?
I mean, just because you use the letter X and Y in both cases, then in the case of the questions that you can't ask and the queries, but okay, I understand it. But the question is, if you have access to you don't have access to the state they share, right? You need to deduce everything from.
Yeah. I need to construct a game that forces them to share some state. And you see here, I claim that at least the CHSH game does it for a single EPR pair. So if they show me that they win the CHSH game with the optimal probability, they must share an EPR pair. Okay? And actually, we will see something stronger. We will see that if they win with an almost optimal strategy, that they share a state that is close to the EPR pair.
Okay. תודה.
בכיף. Okay, hi everybody. We resume the talk. Great. So let's recall what I started talking about. I a bit scaled down the size of the picture so you can see both the definition of MIJ from the previous slide and this C that I defined in the next slide. And I asked what is nice about this C. Okay, and this C is, again, this, you take the original POVMs that you measure with and that are defined. You use the POVMs to decide whether to answer with a 0 or a 1. This is the M's and N's. The M's are for player A, the N's are for player B. And then we defined from them some new operators, the difference between the MIJ to the MIK. Okay, so these were the AIs and BIs. And then we defined this C, which is this sum and the difference of tensor products of these pre-observables, as I call them.
Michael, previously it was the fonts were a bit bigger. I don't know what you did, but
I intentionally wanted you to see both the definition. Maybe I'll do it. I see.
Okay.
Both the definition of C and the definition of the MIJs and NIJs, because I think it was a bit confusing just saying the C without any context. Okay, so let me at least tell you what a part of what C is. Okay, so let's think about what happens if you take C, the conjugate of C, and you multiply it from the left by A0 tensor B0, and you multiply it again by psi. Okay, so let's just open the definition. So by definition, this is exactly a M00 tensor N00. This is psi plus psi conjugate M01 tensor N01, and you multiply it by psi. You add here now you need to take the difference. Okay, this is minus psi conjugate M01 tensor N00 psi minus psi conjugate M00 tensor N01 psi.
First minus is a plus.
Why? No, this is the correct thing. Okay. There are two minuses and two pluses here. If both of them come with the minus, this is
fine.
And now let's check. There are 4 summands here. So just let's check what each of one says. This is the probability that they both answer 0 when asked 0. When asked 0. Okay, so all this scenario is just the fact that the superscripts are 0 is exactly under the case where both of them are asked 0. So from now on, I'm not going to write when they are asked 0. So this is just the probability that both of them will answer 0. This is, maybe I'll replace the color. This is the probability that both answer.
The first two are that they agree when asked 0.
Great. So exactly. The first two are when both of them give the same answer. So this thing is just the probability that they give the same answer. And this is just minus the probability that they give opposite, that they disagree, they give opposite answers.
Right.
Okay? But this is exactly the winning probability minus the losing probability in this case. Because in the case where they are asked 0, they need to to answer with the same answer. So this is just when they are asked 0, 0, this is the winning probability minus the losing probability under this case. But let's look at on this C again. So in the 0, 0 case, we showed that this is the winning probability minus the losing probability. You can check that also in the 0, 1 case and the 1, 0 case, this is the winning probability minus the losing probability. But in the 1, 1 case, this is the opposite, right? They need to disagree. The CHSH game, when X and Y are both 1, A and B need to be different. If A is 0, B needs to be 1, and if A is 1, B needs to be 0, right? So when they are both asked 1, 1, the calculation that we showed is not winning minus losing, is losing minus winning. This is exactly why we took here the minus sign. So at all, like what we have just shown is that exactly that C conjugate times C.
It's win minus lose.
Yeah, exactly. So C conjugate sin C times psi is exactly 4 times probability of winning minus probability of losing. When you use this specific strategy, okay? So we started from some strategy, and the claim is that this number is exactly the winning probability minus the losing probability times 4. The times 4 comes exactly because there's an equal probability of getting a 0, 0, a 0, 1, a 1, 0, or a 1, 1. So if you divide by 4, this is exactly the winning probability minus the losing probability. But we know something about this number, right? We know that this game, this strategy wins exactly with this probability. We will show now that this is the optimal probability, but we know that this is the probability that they win. So you can calculate. This means that this number is exactly 2 square root of 2.
Wait, where did the 4 come from? Why isn't it 2?
Say again?
Why isn't it 2 times this?
There is a 1/4 probability that you will be asked 0, 0, 0, 1, 1, 0, or 1, 1. So actually you calculate here 4 times the winning probability minus the losing probability, because you gave 4 times the mass to any pair of questions. This is these were the winning probability given you were asked, okay, so this is not the winning probability in general. This is the probability of winning given that you were asked 0, 0.
Yeah,
this is the losing given that you were asked 0, 0. But you need to multiply it by 1/4 to get the actual winning probability minus losing probability, right? Because this is a conditional probability. Does this make sense?
Yes, yes.
Great. Okay, so this is what is nice about this C. So I wrote it here. The winning probability minus the losing probability is exactly 1/4 C conjugate C. Great. But now I want to talk about C squared. So now let's assume that this is a projective valued measure. When it's not a projective valued measure, we will see that actually this is an upper bound. So actually the easiest case is that okay. So in the non-PVM case, the non-projective valued measure case, C squared is bounded by the matrix that we are going to calculate now. But what is C squared? Okay, so it has 16 terms, right? Each one of these terms, so we have A naught tensor B naught squared, right? But what was A naught in the PVM case? We said that it was a unitary of order 2, right? So A naught tensor B naught squared is just A naught squared tensor B naught squared, which is just the identity tensor the identity. But this is true for any one of these. When you take the square of each one of these, you get exactly the identity tensor the identity. So you get here, Okay, so I'm erasing this. Get 4 times the identity tensor the identity. Now you have 12 more terms. Okay. So you can just calculate this thing. I will not do all the calculation because I think it's not like we can feel it, but it will consume too much time. And I'll just say that at least under the case where this is okay, and this part is general. This is not dependent on the fact that this is a PVM. This thing was dependent on the fact that this is a PVM, but in general, you just get the additive commutator of A0 and A1, tensor the additive commutator of B0 and B1. So this is just A0, A1 minus A1, A0. And this is just B0, B1 minus B1, B0. So if you open up this C squared, you get this thing. Okay, so let's check what is this is a self-adjoint operator, this C squared. So let's check what is the operator norm of this C squared. The operator norm of C squared is just bounded by the triangle inequality by 4 plus the operator norm of A0, the commutator of A0 and A1, tensor the commutator of B0 and B1. But again, you can just put inside here the operator norm and kill the tensor, and you just get the product of these operator norms. Okay, and this is, you can just check that for a unitary, this is a unitary matrix, and this is a unitary matrix. So the sum of unitary matrices can have only operator norm. It is bounded by 2. So this is smaller or equal to 2. This is smaller or equal to 2. So this is bounded away from 8. But since this is a self-adjoint operator, right? This is just equal to the operator norm of C squared. This is the C star property, right? I think this is the name of this thing. And but what is the operator norm of a self-adjoint?
Why is this the square of the operator norm of C?
Because C is self-adjoint. The A star A op is just the square, the op squared, right? This is, but C is self-adjoint. So
the singular values are the singular vectors,
right?
Eigenvectors.
Yeah, exactly. In the self-adjoint case, exactly. The operator norm is just it's
just the largest. It's just the largest eigenvector
in
absolute value.
Absolute value. Thanks. So this is just largest
eigenvalue. You can come to my class on Tuesday.
In absolute value. Absolute value. Great. So I wrote it here. Okay, so this is what just Nati just stated, that this is just the maximum eigenvalue. So spec C is just the spectrum, the eigenvalues of C. Okay, so this is also a calculation that I started. So we saw that C squared in operator norm is bounded away from 8. What does it mean? It means that largest eigenvalue is bounded away from 2 square root of 2, right? So largest eigenvalue bounded by 2 square root of 2. Okay, so this was just a calculation. I'm getting there. So now what can we deduce from that? Okay, so on the one hand, okay, the fact that C squared op is bounded away from 8 means exactly that this thing always is bounded away by square root of 8, right? This is because the maximal eigenvalue is cannot exceed square root of 8, right? Are you with me? It's okay. So this is a consequence of the fact that the maximal eigenvalue is at most square root of 8.
Similarity maintains eigenvalues. Yeah, it's all in my
why similarity? This is a vector. Nati, this is a number. Size. So, this is not similarity. This is איך קוראים לזה? נו, ההגדרה של ערך עצמי באמצעות
Yeah. This is Rayleigh quotient. Rayleigh quotient.
Rayleigh quotient, thanks, Rayleigh quotient. So this is just comes from the Rayleigh
This is in
quotient.
2 weeks. This is in 2 weeks.
Great.
So again, why is that again? Why is that again? Can you explain again?
Who's asking? This is something, okay. This is a unit vector, right? Psi. This is the inner product. Maybe I'll try to explain it.
What we to say, Michael, this is
the inner product of C psi with psi. So it's just the projection of the image of C on psi times psi, right? In the direction psi, C cannot enlarge psi in its own direction in more than 2 square root of 2, exactly because what I said about the eigenvalue, right? Itai?
Yeah. But psi itself doesn't have to be an eigenvector.
No. But this is a general fact about all vectors. You don't need the fact that it's an eigenvector.
Yeah. Okay.
It's bounded by the largest eigenvector. Quantity.
It's bounded by the projection of C psi on itself is bounded by the operator norm. That's always true.
Right. So maybe it's an easier way to.
I mean, you can really let me do this because I do this in my sleep. The largest eigenvalue of a matrix is the max of XA X transpose over all x's of norm 1.
If it is self-adjoint.
Yeah.
So the inequality is true just because of the operator norm, but the operator norm is actually achieved by psi, which is an eigen.
Yeah, but we had only a bound on the operator norm, so we can't say anything about the relation to square root of 8, right? We know that the operator norm is bounded by square root of 8, so we don't know that actually there is some vector that achieves square root of 8. We just know that all vectors are bounded by square root of 8 in this calculation. Anyway, let's just
wait, Nati, can you repeat? Nati, can you repeat what you said? I missed what you said.
For a self-adjoint operator, even for a symmetric matrix, the largest eigenvalue is the max of XA X transpose. It's the max of the quadratic form over the sphere. The max of XA X.
Okay. So this is exactly.
Yeah, that's exactly what we need here. Okay.
Okay. So
this is called Rayleigh quotient. It's standard. But I have a question, Michael. Yes. So in these calculations that you did before, you gave away quite a lot. So can we actually characterize the optimizer?
This is what we are doing. Like it will take us some time, but the goal is to characterize the optimizer. This is just this is our goal. Okay. Anyway, I'm proving you Tsilson's result. I'm just proving you that actually the value of the game is bounded by this number 1/2 plus 1 over square root of 8. Okay, so this is what I've just done. We saw that this we stated that this number, right, is exactly equal to 1/4 psi conjugate C psi. This is just the winning probability minus the losing probability. But the winning probability minus the losing probability is exactly twice the value of the game using this strategy minus 1, right? Because the losing probability is 1 minus the winning probability. So you just do the calculation and you get the fact that the maximal probability of winning this game is bounded by 1/2 plus 1 over square root of 8. And I will just say a small remark. We didn't use the fact that this is a tensor product at any point, except the fact that the AIs commute AI tensor, the identity commute with the identity tensor BJ for any I and J. So actually, if you also use what we call the quantum commuting model, the same result holds. Okay, so and this is actually the more general thing that Tsilson showed, that even if you use the quantum commuting model, the best winning probability in this game is this number, 1/2 plus 1 over the square root of 8. Great. Now I want to show you something quite nice. We said that the maximal eigenvalue, this is a self-adjoint operator and its maximal eigenvalue is bounded by square root of 8. So this is, if you take square root of 8 times the identity tensor the identity, and you take this minus C, you get a positive operator. And if you take a positive operator, you can decompose it sometimes as a sum of squares. And this is exactly what I'm doing here. I'm decomposing square root of 8 I tensor I minus C as sum of squares. And the claim is that you get this thing. If you do this decomposition, you get 1 over square root of 2 times the sum of these two squares. Okay. Now I'm getting to Nati's question. What can we say if this value is the optimal? If you actually achieve, we started by assuming that you actually achieve the optimal value. The value of this game using this strategy is exactly 1/2 plus 1 over square root of 8. So it means that psi conjugate square root of 8 I tensor I minus C, psi is exactly 0. Right?
Or else the inequality is strict.
Right, exactly. But it means that psi conjugate times any one of these, okay, so let's call this X, large X, and this large Y. So it means that psi conjugate X, okay, I'll not say it like that. It means that X psi is equal to 0. Right, because we had here X squared, we get that psi conjugate X squared psi is 0. This is the number 0, this is the vector 0. Okay, but this is exactly the norm of X pi squared.
Mm-hmm.
Right, so from that, the fact that the only vector with norm 0 is the 0th vector, we get the fact that psi is in the kernel of X, and also psi is in the kernel of Y. But from that, if we move the I tensor B0 to the right-hand side, we get that A0 plus A1 divided by square root of 2 tensor I acts on psi the same way that I tensor B0 acts on psi. And you get the same thing. So this result you get from the fact that X psi is 0, and the fact that Y psi is 0 gives you this thing, that A0 minus A1 divided by square root of 2 tensor I acts on psi the same way that I tensor B1 acts on psi. But from that, this is an easy calculation. You can show that I tensor the positive commutator, so B0, B0, B1 tensor plus B1, B0, acts on psi as the 0th vector. So you get, this is in the kernel of, psi is in the kernel of I tensor B0, B1 plus B1, B0. And a similar calculation gives you the same for the A0 and A1. So what is the conclusion? The conclusion is that B0 and B1 sort of anti-commute in their action on psi. Okay? So this is the conclusion of what I wanted to say up till now. Any questions about this part of the calculation?
Do you have any kind of intuition to what happened here? Because I believe that you did the algebra faster than me, but why would anyone look at this from the beginning? Specifically about
why,
the...
You want something, okay, so the fact that you looked at this operator is exactly because the kernel of this operator is exactly...
especially the next one. Especially the next one. Why should one look on the operator?
Sum of squares?
Yes, the sum of squares, exactly.
Actually, Michal, couldn't we just get it from the, when we did the series of inequalities that got us to a bound on the operator norm of C?
Right.
If we want to get everything tight, then then what we did there must be tight, and part of what
but there you involve all of the operators. Here, the fact that I use this sum of squares, exactly algebraic trick, you can use geometric tricks. Okay, so I attached 2 papers before I started the analysis. There were 2 links, and you can use my slides and just go to the links there. So in one of the links, he gives 2 proofs of this fact, okay? The fact that I tensor B naught B1 plus B1 B naught psi is equal to 0, and the other link gives a third proof, and two of the proofs are algebraic, and one of the proofs is geometric. So I just gave here the easiest proof. I didn't give the proof with the most motivation, because these are very classical things. These are things from the 90s. There are, as I stated now, there are at least 3 ways of proving this fact. And I didn't choose the, I think, the most intuitive, but at least the you can do the algebra and check. So in this sense, it's good, right? Yeah. This was for your question.
Yes, kind of. Like, I don't feel like I really understand, but you say there are visualizations in the paper, so I'll look there instead
You can go there, and also with respect to what Guy just said, if you follow the inequalities, the way I did it, it doesn't give you the result that I stated now. But you can do it in a way and follow and like check more things, use Cauchy-Schwarz and things like that, and deduce that actually these equalities hold. Okay, so I don't know. I didn't want to prepare this geometric part. Maybe I can for some other time, and we will review it together, because it is very interesting. But I thought that it's enough to just show you the algebraic calculation.
Michael?
Yes, Salom.
I couldn't, can you say again a word about how you passed from the third to last line to the second to last line? Like from this?
This is again a calculation. So what do you check? You check the following. So I B naught, what happens here?
Somehow this A0 plus, because A0 plus A1.
You do the calculation. I B naught psi, B naught B1 psi. It's equal to A naught minus A1 divided by square root of 2 tensor B naught psi. This is equal to, now you do it again. You use the other equality. You get, I need to think, you get A naught minus A1 times A1 minus A naught divided by 2 now, tensor the identity psi. You can check that this is the minus of writing it the other way around.
I see, yes, sorry.
And this is exactly where the minus sign gets in. Okay, so this is, again, these are calculations, but, and I think it's not that good that I'm doing the calculations, but at least I show you what you need to do. Okay, anyway. So now we have this property, the fact that the B's anti-commute when acting on psi and the A's anti-commute when acting on psi. So this is the result of what we've done so far. Now I want to talk about what is the conclusion out of this part. So there is this something called the Schmidt decomposition of a vector in a tensor product. So let me review it for a moment for those who don't know what it is. And I'll explain how you calculate this decomposition, okay? So we have some psi inside C to the D, tensor C to the D, right? We can write it in the following form. We can write it as Aij, sum of Aij, EI tensor EJ, right? Where this is the regular, the standard basis of the C to the D. Now you get some matrix. So what is the matrix? The matrix is exactly these Aijs. So if you put these Aijs in the matrix, you get something. And the point is that there is the SVD decomposition of this matrix. Okay, so you can find some unitary basis to the left part of C to the D, and the unitary basis to the right part of C to the D, such that, I don't know, lambda, maybe I need here the star. Lambda star, this is A sigma, where this is a unitary matrix and this is a unitary matrix. And this A is just a diagonal matrix with no negative values on the diagonal. Okay, and this is called the SVD decomposition. Sometimes you see it in linear algebra 2. In Nati's course, you always see it in the mathematical tools in computer science. And my claim is just that there exists this decomposition. This is you can think of it as a black box. And when you use this decomposition, you actually take a basis to C to the D in the left part, a basis to C to the D in the right part, an orthonormal basis. These are the UIs and the VIs. And now the psi, or every psi, the point is that every psi has this kind of decomposition. This decomposition depends on this specific psi, but there exists some orthonormal basis UI and some orthonormal basis VI, such that this psi is exactly some sum, a sum with non-negative coefficients of these UIs tensor VIs. And the point is that the I is the same. There is no sum over I and J. This is because this matrix is diagonal. So you have just a sum over I's of UI tensor VI with non-negative coefficients. Great, this is the Schmidt decomposition. And now let's check what does it mean that I tensor B0 B1 plus B1 B0 acts on psi, the fact that it's in the kernel. So it's equal to 0 on the one hand. This is what we saw on the previous slide. But on the other hand, the identity acts as the identity on the left part, right? But on the right part, it acts exactly like B0 B1 plus B1 B0. It's okay? The point is, no matter what B1, not B1 plus B1 B0 does to VI, you get something that is linearly independent of any of the other terms. Exactly because on the left side, you kept the UI the same. So this is a nice trick to show you that actually, not only that B0 BI plus B1 B0 B1 plus B1 B0 acts on psi as 0, it acts on any vector from this orthonormal basis as 0 if the coefficient is non-zero, if the CI is non-zero. Okay, so this was a mouthful, so maybe I'll give you a moment to stare at it. And
we had just 2 comments, 2 comments and a half. You don't need SVD decomposition because the D is decomposition. The singular value.
Okay, so only SVD.
About this expansion, the U's are an orthonormal basis and the V's are an orthonormal basis. They are not uniquely defined, but the C's are.
Yeah, but okay, you're right, but there
values.
exists some UIs and VIs. That's the only thing I need here.
But the C's...
I cannot resist. After all you said about quantum lo avanti, I cannot resist saying this is exactly the meaning of entanglement.
Really?
Yes, this is what you just said, that it's not unique. This is the non-uniqueness is exactly, so the fact that you have UI and VI on both sides means that if you measure UI, you measure I, you know exactly that the other side is I. This is maximal correlations. But if you can do that in different bases, this is the source. The source of this is entanglement. And this is exactly what you just said, that it's not unique.
Wow, I feel like that character in the Molière play who
that he's speaking prose.
Prose without knowing, has been speaking prose all his life without knowing.
Now we can start.
Okay, you haven't
for quantum mechanics.
You say גם הוא באצילים, אבל.
What? Who's talking? Sorry. Before, no, but someone talked in parallel.
I just said that
Nati.
now Nati can ask for quantum physics grants as well.
Right.
Okay, great. So, the consequence was that if you restrict this B0 B1 plus B1 B0 to the span of the VIs, this is the zeroth operator on this subspace. And my question to you why should we have any space except this subspace? Our unit vector was taken out of the tensor product of this subspace with the others, the span of the UIs with CI is non-negative, right? And my claim is that without loss of generality, you can assume that the original strategy was constructed on a space such that the span of these VIs is the whole space. So let me explain why this without loss of generality is true. Okay, so now I'm claiming that the span of the VI is such that CI is not zero. We can assume that it is the whole space. How do we do it? Just define a projection on this space. Okay, define PV to be the orthogonal projection on this space, and PU to be the orthogonal projection on the UIs, the span of the UIs. And my claim is that if you replace M and N by these PU, M, PU, and PV, N, PV, the value of the strategy did not change. The value of the strategy stays the same. This is exactly what I mean in the without loss of generality, because I have no way of knowing whether this is the whole space of entanglement, right? They can share bits that they don't, qubits that they don't actually use. But I care only about the qubits that I actually use. So in this sense, I can restrict my view only to this space. So I assume now without loss of generality that the original C to the D was just this span of the VIs and span of the UIs. Okay, this point is clear?
Yeah, so in other words, that B0 and B1 anti-commute.
Oh, exactly. So now I can just say, okay, so these B0 and B1's anti-commute. Great, thanks, Nati. This is what is written here. B0, B1 plus B1, 0 is the zero operator. It's not acting on something in a zeroth way. It's just the zeroth operator on C to the D. What, Alon? You wanted to ask something?
I mean, you will also want to show us that in fact UI are equal to VI, or will not? Like you wanted
no,
to
this I don't need that. I don't need that UI is equal to VI. There is some isometry that sends the UIs to the VIs, and this is okay by me. Everything here is up to an isometry of the space, but choosing a different basis is just taking an isometry, right?
Okay.
Okay, anyway, my claim is the following. Forget the fact that we used PVMs, projective valued measures. My claim is that even if you take POVMs and you achieve the maximum value, the optimal value, you actually used a projective valued measure. So any positive operator valued measure that is not a projective valued measure cannot achieve the optimal value. Okay, so this is my claim now. So we can assume also without a loss of generality that actually these AIs and BIs are unitaries and not only pre-observables, there are observables in the definition that I gave last time. Okay, so the way I'm proving it is the following. Okay, so I'm not going to write it now because I'm lacking time. So what do I need to show? I need to show that the eigenvalues of the A's and B's are just plus or minus ones. If they are strictly pluses and minus ones, this is a projective valued measure, and the eigenspace of ones is one projection and the minus one is the other projection. Great. So the spectrum of projective operators of positive operators that sum up to the identity is bounded between -1 and 1. So actually it's bounded between 0 and 1, right? But let's take just, this is enlarging of the possible choices of a spectrum. Sorry, I stated something wrong now. Okay, so if we have M and N, okay, so we had these M0, 0 minus M0, 1. This is A0, right? I want to say something about the spectrum of this thing. My claim is that the spectrum of this thing, since M00 plus M01 is the identity, I'm claiming that A0, the spectrum of it, spectrum of A0 lives inside -1, 1. Okay, so these are, I think this is like functional calculus. How can I explain it in the easiest way?
Because M0, I mean the operator norm. Sorry, never.
Yeah, this goes back to my convexity, supposed convexity argument. I think I'm not sure that it's true, but it feels true that the measurements are that the set of measurements is convex, and its eigen and its extreme points are projection.
No, but I don't want to go there. I don't want to give some ad hoc explanation. I want to give something that's a bit more concrete.
I think that's okay. That's not concrete, but I don't think it's ad hoc. I think it's like this is their reason, assuming it's true.
It's the opposite of ad hoc. You want something ad hoc.
Yes. Fine. Yeah, I'm fine with ad hoc.
Okay. Anyway. I claim that the spectrum of these A's and B's, even in the case of the POVM, is bounded by -1, 1. So you cannot get values outside of this thing. And you can check from Cauchy-Schwarz and this. Okay, so I'll go back to the C. When we calculated this C squared, I said that this thing only happens when this thing always happens. This calculation is always true. But this thing actually bounces from above what actually you get here. So you get A0 squared tensor B0 squared plus A0 squared tensor B1 squared and so on. So you get these 4 operators, and each one of them is bounded away from 1 from above. I'll get back down. Sorry for that. And if you just apply Cauchy-Schwarz to this equality, you get these 4 conditions. Okay, so to get the maximal, the optimal strategy, you must have that A0 tensor I psi, the norm, the 2 norm of this thing is equal to A1 tensor I psi is equal to I tensor B0 psi and so on, which are all equal to 1. Okay, so you must have this thing. But again, you can look at the Schmidt decomposition. What does it mean that A0 tensor I psi? What does it do? What it does? It acts only on the left part of the Schmidt decomposition, right? The right part stays the same. So to have the same norm, if you want to conserve the norm, the only thing you can do is just permute the UIs if you act with the A0, or permute the VIs if you act with the Bs. So if you have a permutation, all its eigenvalues sits on the unit circle. So this is just the unit circle. If you take the unit circle and take the intersection with -1, 1, you get -1 and 1. This is all you need. Okay, so again, this is maybe there is some convexity argument, but I claim that this is basically linear algebra. You just use Cauchy-Schwarz on our previous calculations, and you get what you need. Okay, that these are projective valid measures actually. Any comment? Something? Okay, we are about to be done. Now, the group theorists in the audience should be happy because we are going to talk about representation theory a bit. What actually we did is show that these A0s, these A's and B's are a representation of the dihedral group with acting on the square. Okay, so this is just the set of isometries of the plane that preserves the unit square. And this is not any representation of D4, because we showed not that A0 times A1 to the usual presentation of D4. You can take a presentation of D4 with two elements, so x and y, such that x squared is equal to y squared is equal to 1. And what we need that xy is the inverse of yx, right? Yx inverse. No, I'm writing something wrong. No, this is not what I want. I used a different representation. I want that xy to the fourth or something is 1, right?
Yes, I think so.
Yeah, so this is the presentation of D4 using two involutions, like taking this involution with respect to this line and with respect to
reflections
this line.
along
reflections.
Yeah.
Okay, great. So this is D4. So, but we showed a stronger thing. We showed that actually in this representation, xy plus yx is equal to 0. And there is only one irreducible representation of D4 that satisfies this condition. And this is up to an isometry, it's just taking these two matrices. Okay, so there is a single irreducible representation of dimension 2 that satisfies this relation, and up to an isometry, up to some choice of basis, these are these two matrices. So actually, we can take an isometry of our spaces, some phi and phi prime of these C to the D, such that when we act with phi on C to the D, we get these two matrices that are written here, and we do it on the right register, on the C to the D on the right. And we use some other isometry that takes this representation. So this is a different representation, but it's the same irreducible representation, but with taking a basis that is oriented 45 degrees. 22.5 degrees maybe. Anyway, this is another representation of D4. Great, so the point is that up to an isometry of the space, so you have some length preserving linear transformation of your space that sends A0 to this thing, A1 to this thing, B0 to this tensor, the identity, and B1 to this tensor, the identity. Okay, cool. And now we get to the point of something that Dorit said at almost the beginning. You can check that actually for psi to give you a perfect, an optimal strategy, this X tensor I acting on psi, you need actually X tensor, the identity on the rest of the space, but this is the same. X tensor I acting on psi needs to be the same as I tensor X acting on psi, and Z tensor I acting on psi is the same as I tensor Z acting on psi. But this means that psi is an eigenstate of both X tensor X and Z tensor Z, but there is only one up to a phase, okay? So you can multiply it by some element of the unit circle, but up to some phase, there's only one element, unit vector that is an eigenvector with eigenvalue 1 of both X tensor X. This is the matrix X, and this is the matrix Z. So there's only one element that is in the that has eigenvalue 1, both for X tensor X and Z tensor Z, and it's the EPR pair. So what actually we got here is that a perfect, an optimal strategy forces the players to share an EPR pair. They must use an EPR pair up to an isometry. So they can change bases. They can add some qubits that they don't actually need. They can have some auxiliary things. So all this, you get actually an EPR pair tensor, I called it rubbish last time. So some things that you don't actually act on. but the only thing you act on is an EPR pair if you use an optimal strategy. And at least at the beginning of next time, I'll explain, okay, so we can show now that there is a game that forces the players to share a single EPR pair. Next time, I'll talk about how can I force them with the same idea, with representation theory, how can I force them to share, firstly, a polynomial amount of EPR pairs, and then this will be much harder, and actually, at least for now, there is no representation theoretic explanation, just a proof of Natarajan and Vidic that it works. How can they share exponentially many EPR pairs? And I will talk more about this part next time.
Okay, about next Sunday, you're going to send out the message asking what people.
Yeah, so I again ask if any one of you have a problem with next Sunday, please inform me, and we will decide according to your messages whether we do meet next time or not.
So just for the eigenstate is the same as eigenvector, right?
Yeah, eigenstate is just another name of an eigenvector. Just when I say it's a state, it's a unit vector and not just an eigenvector. Okay.
So you told us that you will prove that we need to use an EPR pair, but what you actually did was reduce to a representation problem, and then just came out.
No, why did I reduce to a representation?
Right, you're saying that the only representation of the dihedral group that satisfies.
Yeah, you are right. Okay, so I wanted to claim something about states, but I actually showed you something about the measurements, and from the structure of the measurements, I deduced something about the state. And this is the way we do it all the time, like in at least in the papers that the word we is not good here. The way they do it in their papers is that they prove some group theoretic structure on the measurements, on these observables, on these M0 minus M1 and so on. And from this structure, they can show that the only eigenvalue one eigenvector is the either EPR pair or tensor product of EPR pairs. And this is the way you deduce something about the EPR pairs.
All right, but generally these proofs, maybe for the dihedral group it's easy, but generally these are difficult things to understand. Right? Okay,
so there are two things that we need to actually say. First of all, what happens to something that is when you use something else than the dihedral group? Okay, so this is the first thing. The other is, what if you don't have an optimal strategy, but only an approximately optimal strategy, right? You cannot, if you do only a few rounds of your game, you cannot distinguish between these two cases. And this is called, okay, so what actually we showed here is called self-testing. And when you want to say something about approximate strategies, it's called robust self-testing, and it's closely related to stability theory in groups. And actually we will need...
What's the claim for the dihedral group? That you also have this stability and robust self-testing?
There is only one representation, which is with this property of AB plus BA is B not B1 plus B1 B not is equal to the minus I. There's only one E-rep that satisfies that, and thus your representation, if you decompose it to irreducible representations, it's just the sum of these representations, meaning that the matrices are just these matrices, these specific matrices tensor the identity, okay, up to some isometry. So this is something very dihedral group phenomenon.
Specific.
Specific, yes. And we will show that a similar thing happens to the powers of the dihedral group. If you take just products of the dihedral group with itself, you will get a similar phenomenon, okay? And I think this is the dihedral group part. But actually, we will need something that states that if you have an almost representation, so we will show that almost optimal strategies generate almost what we called epsilon representations when we talked about conservative problem. And we want to fix an epsilon representation, and this will be something that is very general. So for any finite group, you can fix an epsilon representation to an actual representation by enlarging the space that you act on by only a bit. This is a result of Gowers and Khatami, and we will discuss it next time.
Okay, thanks.
תודה רבה.
תודה.
So see you next week, maybe. Send me emails if it's a problem.
See you or see somebody else.
Yeah.
Thank you.
Ciao.
Bye.
Michael?
Ken.
I just wanted to ask the question, like maybe a bit too before, but so you mean that if you have, say, two players and on Alice and Bob, and you know that somehow the state that they share is, if you look at its Schmidt decomposition, you see like all lambdas are there, like it has full.
Yeah.
Then you tell me that we can change up to an isometry on one of the spaces so that you get the EPR state. This is basically what.
No,
like,
that's not true. No, you need all the lambdas to be the same for that to happen.
Ah, okay, yes, of course. And
yeah, but I get a weighted, but I got a weighted thing, right, Dorit? You will get a weighted. I don't understand. So something.
You could have different weights.
I mean, think of lambda as 0 and 1 and 0. Like you will. No,
but when I'm saying that you take the EPR per tensor, some auxiliary state, right? The auxiliary state can tell you something like from this 2x2 part, I'm taking something, and from like I can. No, maybe I'm.
Sorry, I may not understand the question. If you have a state on more qubits, the number of qubits is larger, then you probably can write it as an approximation of a tensor product of an EPR state times some state which is not uniformly a uniform superposition. Mm-hmm. And then you can deduce some kind of, I mean, you do have a smaller number of entanglement bits. I mean, you will have some entanglement, some maximal entanglement, but not maximal on the entire dimension. Mm-hmm. What I was saying,
and I think this is what I deduced here, right? Or wait, like I showed something only about. I showed that I can decompose my space in such a way, such that it is the tensor product of two things. All my operators act only on. Like I decompose the space such that it has a left register and the right register, and I act only on the left register. And in the left register, they genuinely share an EPR pair, and I know nothing about the right register. And maybe the right register is a mushpa.
Influence. But where did you show
that? This is exactly what I showed now. My claim is that the psi. Okay, so first of all, you have some isometry that sends A0. You can just forget about this A0 and A1 and so on. You can assume that the A0 is just this matrix, this 1 over square root of 2, 1, 1, 1, minus 1, tensor the identity on the D over 2. So this is just blocks of this matrix, right?
Yeah.
And similarly, that the BIs are just these matrices on the block, on the diagonal. So up to some isometry of your space, A0, maybe I'll say what B0 is. B0 is just 0, 1, 1, 0, 0, 1, 1, 0, 0, oops, 1, 1, 0.
Yeah.
On the block diagonally. Okay, and now I claim that also the following. You can see that A0. Okay, so you can check that, okay, so actually B naught, I'm writing B naught on the left-hand side because it's now this specific matrix. If you look at B naught, how it acts on psi, it's just psi.
For EPR, for the EPR state.
For our state.
For the one that achieves the maximum.
The fact that we achieve optimal value means that this happens. And also for B1. B1 psi is equal to psi. But from that, you can deduce that psi is EPR tensor auxiliary.
Okay, yeah.
But the auxiliary, in some sense, what does the auxiliary does? It says that, I don't know, like in the first 2 coordinates, you have an EPR. In the second 2 coordinates, you have an EPR. In the right? In every 2 coordinates, you have an EPR, but it's weighted in some sense. The aux is exactly the weights. So I don't think you actually need, in the Schmidt decomposition, I need to think about it. Maybe I'm wrong, but in the Schmidt decomposition, you can have CIs that are not the same in this case.
Yeah. I was just saying that I was just responding to Alon's question that in order to see this phenomena, you have at least to have an EPR state in which the lambdas must be the same. But if you take a tensor product with an additional state, there's no restriction on that additional state. So overall, the lambdas could be very different, but still you need to, there needs to be an entanglement hidden in there, an EPR state.
Yeah.
Okay.
And actually an important point, and I don't know if no one asked it, but I just want to state it, that an important point is that we only act on the EPR part. So this auxiliary, this rubbish that is on the right register, we don't measure it. The strategy cannot use this auxiliary part. If it could use the auxiliary part, it's not an auxiliary thing, right? It's necessary in the calculation. But the claim is that we don't actually measure anything about the auxiliary part. We measure only things about the EPR pair.
Yeah, this ties nicely to how you would say POVMs are dilated to PVMs up to an auxiliary state.
Right, we add, so throughout these kind of proofs, we will add auxiliary states, right? When you go from, you use Nymax dilation, you add an auxiliary state. You use then these kinds of stability and robust self-testing, you get another auxiliary state. So you add more and more auxiliary states, but you don't actually act on them. So at the end, you will just deduce that you know how do you act on the part that you actually are interested in.
But by the way, a smaller remark, like this thing we struggle to explain, like if the sum of, like you had 2 positive operators which sum up to the identity, you wanted to say that the spectrum of the difference is between minus
1 and 1. Yeah.
Yeah. So, I mean, I don't think it's very trivial, or I can recall the proof now, but there's a proposition which says it, like I can send it to you.
Okay.
I mean,
I was sure it is true, and I convinced myself that it's true when I prepared the lecture, but it was too long ago and I didn't re-prepare this part of the calculation. So
yeah, it's a funny thing.
I was convinced it's true.
Yeah. Yeah. No, it's like a funny thing where, yeah, okay, בסדר.
Cool.
Okay, תודה. Thank you.
אחלה. טוב, ביי, נראה לי שכבר...
אוקיי.
נכון, גיא, אין לך מה שרצית שנדבר עליו?
מה זה?
לא רצית שנדבר על משהו, כלומר נשארת פשוט כי נשארת.
סתם נשארתי, כן, לא יודע למה.
כן, אחלה, יאללה, ביי.
ביי.